Hello guys, in this video we are asked to find the value of a for which this integral is equals to this constant, right? So we are going to start off by rewriting this integral. So we have the integral from 0 to the tan inverse of a, right? Of cosine of 2x can be written as the cosine square of x minus the sine square of x. This is from the double angle identity divided by the sine square of x plus 3 times the cosine square of x dx. All right, cool. Now we are going to use the substitution. We are going to let y to be equal to the tangent of x. This is obvious. So when we do this, what is x? X is going to be the tan inverse of y, and then dx is going to be equal to 1 all over 1 plus y squared dy. This is an expression for dx. Now the change in limit, right? When x is equal to 0, which is the lower limit, we have y to be equal to 0, which is the tangent of 0. And when x is equal to the upper limit here is the tan inverse of a. We have y to be equal to the tan of the tan inverse of a, right? Tan of the tan inverse of a, and that is equal to a, because this and this one will cancel out nicely. So those are the change in limits. What about an expression for the cosine square of x and the sine square of x in terms of y? So let's do that now. From our substitution, we know that y is equal to the tangent of x. This is what we used. Now let's square both sides of this substitution. When we do that, we have y squared will be equal to the tangent square of x. Right, so let's add 1 to both sides of this substitution. When we do that, we have 1 plus y squared, which is equal to the tangent square of x plus 1. From the Pythagorean identities, the tangent square of x plus 1 is the same as the secant square of x. So that means that 1 plus y squared is equal to the secant square of x. So this can be written as 1 all over 1 plus y squared, and this is the same as 1 all over the secant square of x, which is equals to what? 1 over secant square of x is the same as the cosine square of x. So 1 over cosine is secant, 1 over secant is cosine. So this is what we have. So in place of the cosine square of x, I'm going to replace it with that. Now what about the sine square of x, right? So the sine square of x, we know from the Pythagorean identities that the sine square of x plus the cosine square of x is equals to 1. So that means that the sine square of x is the same as 1 minus the cosine square of x. So we have this, we can find the sine square of x in terms of y, and that is 1 minus cosine square of x, which is 1 all over 1 plus y squared. And then sine square of x is the same as 1 plus y squared minus 1 all over 1 plus y squared, and that is equals to y squared all over 1 plus y squared. So we have an expression for the sine square of x and the cosine square of x, all in terms of y. Now the integral in the y world will look like this. I is going to be the integral from 0 to a. Now those are the limits of integration for y, right? All right, of cosine square of x minus sine square of x. Cosine square of x is this, which is 1 all over 1 plus y squared, minus sine square of x, which is y squared all over 1 plus y squared, divided by sine square of x plus 3 times cosine square of x. Sine square of x is y squared all over 1 plus y squared, and cosine square of x is 1 all over 1 plus y squared, like that. And this is multiplied by dx. An expression for dx in terms of y is that is 1, this is multiplied by 1 all over 1 plus y squared dy. The integral is now entirely in the y world. So now let's solve this. We have the integral from 0 to a of the numerator is 1 minus y squared divided by 1 plus y squared. What about the denominator? The denominator is 3 plus y squared divided by 1 plus y squared, right? And this is multiplied by 1 all over 1 plus y squared dy. So the integral here is a bit short, so we can make it longer. Why not? So this is the integral from 0 to a. There's going to be a cancellation. This one is going to cancel this one out nicely, right? And then we have the integral. The numerator is now 1 minus y squared, and the denominator is now 3 plus y squared. And this is multiplied by 1 all over 1 plus y squared dy. This is from 0 to a. Sorry about that. So I is going to be equal to the integral from 0 to a of 1 minus y squared all over 3 plus y squared multiplied by 1 plus y squared dy. Now next task is partial fraction decomposition. We are going to use partial fraction decomposition to split this. This is multiplied by 1 plus y squared. So because we have quadratic terms at the denominator, the numerators are going to be the linear terms, and we have cy plus d. So the first one is going to be divided by the first factor 3 plus y squared, and the second one is divided by the second factor 1 plus y squared. And then we have 1 minus y squared all over 3 plus y squared multiplied by 1 plus y squared. And this is equal to, let's do cross multiplication now, ay plus b. This is multiplied by 1 plus y squared plus cy plus d. This is multiplied by 3 plus y squared, like this. All this one is divided by the LCM, 3 plus y squared multiplied by 1 plus y squared. The denominators are the same, so the headache now should be how to equalize the numerators. So 1 minus y squared is equals to, now let's FOIL. We have ay, right, plus ay to the third plus b plus by to the second plus 3cy plus cy to the third plus 3d plus dy to the second. So this is what we have now. Let's scatter like terms. So 1 minus y squared is equals to, we have a plus c. This is y to the third. That is this and this, right? And now the y squared terms, we have b plus d. This is y squared. What about the y terms? We have a plus 3c. And then we have the constant terms, which is b plus 3d. Cool. Now let's compare both sides. So by comparison, we have a plus c, which is equal to 0. There is no coefficient of y to the third on the left. We have b plus d. This is equals to -1. The coefficient of y squared on the left hand side is -1. The y term, we have a plus 3c, and that is equal to 0 as well. There is no coefficient of y on the left hand side. And the constant term, the one without the y, 3d plus b, and this is equals to 1. The constant term on the left hand side is equals to 1. Cool. Now solving these four equations simultaneously, the values of a, b, c, and d that will satisfy them will be a is 0, b is equals to -2, c is equals to 0, and d is equals to +1. So now that we have these values, you can verify that these ones will satisfy all the four equations. So I'll leave that to you to verify. Now let's go back to our partial fraction and plug in the values. So our expression is 1 minus y squared. All this one is divided by 3 plus y squared. This is multiplied by 1 plus y squared. And this is equals to ay plus b, right? A is already 0, so 0y plus b, that is just going to be -2 on top, divided by the first factor, 3 plus y squared. The next one is cy plus d divided by 1 plus y squared. C is 0 plus d, so that's going to be 1 all over 1 plus y squared, the second quadratic term. So this is equals to what really? So we can now integrate our integrand. So we have the integral from 0 to a of this, which is the same as that, right? So we are just going to integrate. So I is going to be the integral from 0 to a of this, which is the same as this. So we now have to integrate this one to all over 3 plus y squared, and then plus 1 all over 1 plus y squared, like this. All this one dy. Let's split this integral into two different integrals. We have the -2 out, So permit me to write it like this. I have the integral from 0 to a of 1 all over 1 plus y squared dy, and then minus 2 times the integral from 0 to a of 1 all over y squared plus 3 dy. Alright, so the first one is familiar, that is the tan inverse of y, right? So let me write it again and then simplify the second one. So the second one is going to be 2, the integral from 0 to a of 1 all over y squared plus 3 can be written as the square root of 3 squared, right, dy. And now comparing this one to the arctan integral, we have the integral of 1 all over x squared plus a squared dx. This is 1 all over the constant a and then multiplied by the arctan of x over a. Alright, so now let's solve this integral. I is going to be equal to, this one is the arctan of y. The limits of integration from 0 to a minus 2 times, this is 1 all over a is the square root of 3, and then we have the arctan of y over the square root of 3. The limits of integration from 0 to a. And now let's put in the limits. Putting in the lower limit, you are going to have the tan inverse of a minus 2 over the square root of 3. Putting in the upper limit for the second one is going to be the tan inverse of a over the square root of 3. 0 for the lower limits. For the first and the second one will be 0. So this is what we have for the resulting value of the integral. And now for me to find the value of a, I will have to now equate the resulting value of the integral to this constant that is given to us to enable us find the value of a. So that is 2 minus the square root of 3 times pi. So I'm going to equate this one. So the resulting value of the integral is the tan inverse of a minus 2 over the square root of 3 and then multiplied by the tan inverse of a over the square root of 3. I'm going to equate this one to the resulting value of the integral, and the resulting value of the integral is 2 minus the square root of 3, all this one times pi divided by 6. Alright, so now let's solve for the value of a by doing simple comparison. So the tan inverse of a minus 2 over the square root of 3, and then the tan inverse of a over the square root of 3. This is equals to 2 pi over 6 minus the square root of 3 pi over 6. So the idea is that the first one here is equals to this, and the second one is equals to that, because you have the negatives separating them. So now let's do the comparison, right? So we have the tan inverse of a. This is equals to 2 pi over 6, and that is equals to pi over 3, right? So if you want to get a, we have to take the tangent on both sides. So the tangent of the tan inverse of a, this is the same as the tangent of pi over 3. Just taking tan on both sides, nothing amiss. So we have a to be equal to the tangent of pi over 3. And tangent of pi over 3 is the tangent of 60, which is the square root of 3. So this is the value of a in the first comparison. Now let's compare the second one to see whether we get square root of 3 as well. Alright, so the second one is that 2 over the square root of 3. This is the same as, 2 over the square root of 3 times the tan inverse of a over the square root of 3. This is the same as the square root of 3 times pi over 6. Alright, so now to get a, we have to multiply both sides by square root of 3 over 2. Do that here, and I'll do that here to maintain equality, right? So this cancels that, and that isolates the tan inverse of a over the square root of 3, and this is equals to, multiplying this one is going to be 3 pi on top over 12, and that is equals to pi over 4, right? So I have to take the tan on both sides. So the tan of the tan inverse of a over the square root of 3, and this is equals to the tangent of pi over 4. And then this will cancel this one nicely. Then we have a over the square root of 3, and that is equals to tan of pi over 4 is tan 45, which is 1. So that implies that a is equals to the square root of 3, which agrees with the comparison in the first one. It agrees with the answer that we got from the first comparison. So now we can conclude boldly that a is equal to the square root of 3. So this is the value of a for which that integral is equal to that result. So when we go to the top, we see that the value of a here is equal to pi over 3, square root of 3. I'm sorry about that. So when we replace a with the square root of 3, we have the tan inverse of the square root of 3, and that is going to be equal to pi over 3. So this upper limit is pi over 3, because when a is equals to square root of 3, the upper limit is going to be pi over 3. So when you integrate this integrand from 0 to pi over 3, this is the result that you are getting. Thank you for watching this video. If you really find that helpful, consider subscribing to Calculus Diaries and give me a thumbs up so that I'll continue uploading engaging tutorials on integrals. I thank you and I'll see you in the next one. Bye bye.